Morning, everyone. How are we doing? Questions while we wait a moment or two for people to come in? Anybody? No? We're good? Questions on graphing? Today we're going to do optimization. These are word problems. You have all the required knowledge to tackle them. We're just going to do a few to get you going. Morning, everyone. Come in, come in. So optimization is what we're doing. Have we covered all the content that will be on the exam? Not yet. Today, new stuff, but again, not really new. I mean, it's new to us, but like I said, you have all the required knowledge to tackle it. We're going to look at integrals, which we kind of introduced anyways, right? So again, there you have all the knowledge required as well. And maybe we'll do Newton's method, we'll see. Jacob is asking on the final, is it good enough to find the slant asymptote, or do you need to prove it? You need to justify all your work. Absolutely. There will not be any epsilon delta on the final. Right? Just saying something is a slant asymptote is not good enough. You need to prove it using the definition. So you need to show that the limit of f minus mx plus b is equal to 0. Questions? Shall we get started then? Optimization. Like I said, we have all the required knowledge. Optimization refers to, I believe I did upload, Michael, solutions to the midterm. So have a look at that. So optimization refers to word problems that ask you to maximize or minimize something, perhaps both. Let's just right away go into some examples. Find two numbers. whose difference is 100. Difference is 100, and whose product is a minimum. Find two numbers whose difference is 100 and whose product is a minimum, right? A typical, well, I mean, an easy, it's number 2. So, an easy example of what we're referring to here. So, let's introduce some variables. Let x and y be two real numbers. What do we want? We want the difference to be 100. So x minus y is 100. And what do we want to do? So we want two numbers whose difference is 100 and whose product is a minimum. So minimize the product xy. Right, so you see what's happening, right? Just view this way, you have a function of two variables. But you have this as well. Michael, I suspect Isabella, or, well, I mean, let me say this. Not only did I upload solutions, but I also uploaded a marking scheme. So have a look at the marking scheme as well. The marking scheme will tell you where the marks were given. So, right, I mean, here you have an equation involving x and y. So you can solve for one in terms of the other. And then you can plug that in. And what we want to do is to minimize, so you know exactly how to do that. Matt is suggesting x is 100 and y is 0. Maybe. Let's see. And plus, you know, you don't just want to give something, you have to justify that it's a minimum here. If the question didn't explicitly say real numbers only, what is that I there? I, the imaginary numbers? No, I mean, of course here, you know, this is only count 1. We're not dealing with complex numbers. So real numbers, even if it doesn't say real, you know that it's real. So here y is x minus 100. And plug that in. And you know how to maximize and minimize these things. You're going to take the derivative. You're going to look at critical points. you're going to justify that what you have is an absolute max or an absolute min using the first derivative chart. If you take a number less than 50 and plug it in, it's clear that the derivative is going to be negative. And if you take a number bigger than 50 and plug it in, it's clear that the derivative is positive. So you see what's happening here. At 50, you have an absolute minimum. Questioner was asking for two numbers. When x is 50, y is negative 50. And your product is negative 2,500. This is the smallest product you can have. Right, so no guesswork, no trial and error, complete work, fully justified. Very nice. Jonathan is asking, can we set x as x and y as x minus 100? Well, that's really what we did here, right? It's exactly what we did. And I mean, I understand you're possibly hoping to save a step because this is an easy example, but like I said, it's number 2, so it doesn't get any easier than that. Eventually, these get harder and harder, and you don't want to be skipping any steps. So let's not do that in the beginning either. What is the minimum vertical distance all good? Here it is. What is the minimum vertical distance between these two functions? What does that even mean? Right, let's graph these quickly. You know what this looks like, right? Parabola. It's y equals x squared, but just moved up by 1. And then this parabola, which is negative x squared plus x, which has the x coordinate of the vertex, negative b over 2a. So add 1/2, when x is 1/2, this is 1/2 minus a quarter, which is a quarter. And this goes down, right, because of the negative x squared. And it does go through the origin, also when x is 1. There it is. So you understand what the question is asking, right? The question is asking, if you fix any value of x, you can calculate this distance right here. The distance between the two parabolas, the vertical distance. The question is, which distance is the smallest? It's not immediately clear. So which distance is the smallest? What is the distance? Right? This is really the distance between the two y values. It's the distance between the two y values. The distance between the largest y value, well, the y value on top minus the y value on the bottom. This one is always on top. So the distance is this minus that. The difference between, exactly, Michael, the difference between the two y values. Or, if you prefer, 2x squared minus x plus 1. Would it matter which one you would subtract? Absolutely, right? Absolutely, because we want a distance, so we're expecting a positive answer. If you did one minus the other, the distance would always be negative, and there wouldn't be a smallest one, right? In fact, in that case, you might ask, what is the largest distance? So if you're looking for minimum here, it's large minus small. While smallest in magnitude, in that case, you would introduce absolute values, and then you have an issue, right? You know that absolute values aren't differentiable, so you actually have to get rid of the absolute value in that case, and it just makes things more complicated. So there it is. Differentiate. What is the derivative? 4x minus 1. Critical points can easily be read off. X is easily seen to be 1/4. And let's draw a first derivative chart to see what's happening, right? Because you see the issue. Here they're asking for minimum. They were asking for minimum in the previous question as well. In another question, they're going to be asking you for the maximum. So how do you know that the critical point always gives you what you want? You don't. You don't. You have to justify. So if you take a number less than 1/4, maybe 0, the whole thing is negative. And if you take a number bigger than 1/4, maybe 1, the whole thing is positive. So you see that you have an absolute minimum occurring at 1/4. If it's a maximum, when you want a minimum, then what do? Well, then there's an issue. There's an issue. Maybe you can argue that there is no minimum by looking at your function, and maybe suggest that the question is incorrect. Right? Suppose here that they had been asking for the maximum vertical distance. Well, it's easy to see that the distance is getting larger and larger. And as x goes to infinity, you can show with relative ease that this limit goes to infinity. And consequently, there is no maximum vertical distance. But there is a minimum, and it occurs when x is 1/4. The question was, what is the minimum vertical distance? So we have to really answer the question, right? Let's not lose track of what the question is asking. Minimum vertical distance it occurs when x is 1/4. So what is that? 1/8 minus 1/4. That's 1/8 plus 1. Wait, 1/8 minus 1/4 is minus 1/8 plus 1, 7/8. Is that correct? 7/8? Michael, point that out to Sean or Isabella. They'll take care of it. How are we doing here? Questions? Consider the following. Find the dimensions of a rectangle with an area of 1,000 square meters, where the perimeter is as small as possible. Right, and Michael brings up the interesting point, which is why we have released the midterms and why we have released both solutions and the marking scheme. Marking on CrowdMark, it takes its toll. And, the TAs have a lot of marking to do. And sometimes you don't see the obvious. So have a look at the midterm. Make sure there are no mistakes in the marking. And if there are, get in touch with Sean or Isabella and they will take care of it. Well, I know you're kidding, but TAs are still students themselves, and they, very much like you, have courses, have midterms, have everything that you do, and more, right? They are graduate students, so the courses are arguably harder. It's and it's just as difficult for them as it is for you. So let's all be lenient, and if there are mistakes, we will address them, and no worries. All right, consider this. Find the dimensions of a rectangle with an area of 1,000 square meters where the perimeter is as small as possible. FD is asking if the final is going to be harder than the midterm. Well, I mean, look, it's harder by the fact that there's more material, right? The midterm only covered about a third of the actual material. So more content, as Morgan suggests. And consequently, following that, it has to be more difficult because there's more things to learn. But the questions themselves will not be more difficult than the midterm. How do I recommend preparing for the final? Doing lots of exercises from the book. Master the material. And if you are very comfortable with the material, there's no reason for you not to do very well. And then when should you start? You should start right now. I mean, you should have started in September by keeping up with the material and doing lots of exercises right after class. But, you know, it's never too late to start. Plus, this leads me to to something I was going to forget. If you did not do well on the midterm, first of all, treat it as a wake-up call that you probably need to work more. And let's take this time to announce an alternate grading scheme for those who did not do well on the midterm. If you do better on the final, we will transfer the weight of the midterm onto the final. There's no need to sign up for this alternate grading scheme. We will calculate both marks and attribute the highest one. The final might not have as many variables as the midterm. I want to say that is still true, yes. So only the no, Elizabeth, not the highest of the two exams count. If you did well on the midterm, that midterm mark still counts, but you still have to do the final. So it's not the highest of the two, but rather, if you do better on the final, then the final will count for midterm and final. I want to make the length a bit shorter. So, I mean, again, I have not even started to write it, but yeah. Yeah, so as Morgan says, if you have a higher grade on the final, it replaces the midterm. So the final will be 70%. And you will have 72 hours. All right, everybody's excited to do this question. Let's do it. And I mean, you recognize immediately real world applications, right? Suppose you want to enclose a field for your farm animals, and you want that field to be 1,000 square meters, but you know, you're frugal. You don't want to spend too much money on a fence. So you are looking for the smallest perimeter that still encloses an area of 1,000 meters. So, you know, let's draw your rectangular field, and doesn't really look like a rectangle, but let's believe it is. Worst rectangle ever. Better? Better. Let's introduce some variables. I mean, we don't know the length and the width. So let's call them x and y. What do we want? We want to minimize the perimeter. What is the perimeter? The perimeter is 2x plus 2y. Minimize this perimeter subject to the area which is xy, but the area has to be 1,000. Right? So in other words, buffering, oh, just wait a moment, hasn't buffered for a while, right? We're back? Is everybody back? Let's wait a minute. Very good. So we have the area xy is equal to 1,000. So it's easily seen that y is 1,000 over x. Do we want to introduce some domain for x, right? This being a physical problem, we certainly don't want a negative length, negative side for x, right? Negative side of a rectangle. So of course x should be bigger than or equal to 0. But if x is 0, the area cannot be 1,000. So you cannot have 0 there. So x should be bigger than or equal to 0. And consequently, your perimeter, 2x plus 2y, well, y is this, so 2,000 over x. And we want to minimize that. You know exactly how to maximize and minimize functions. You take the derivative. The derivative is 2 minus 2,000 over x squared. Let's put everything over common denominator. 2x squared minus 2,000 over x squared. Maybe factor out a 2. And we see immediately what the critical points are. What are they? You tell me. Zero from the denominator and plus or minus root of 1,000 plus or minus 10 root 10. But not the minus, thank you, Sheila. Not the minus and not 0 either. Exactly that. So really only one critical point, as Seelan pointed out, root of 1,000, which is 10 root 10. Well, as you know, you're not going to stop there. You need to justify. You need to justify that this is a minimum. And we can do so by looking at the first derivative chart. We are restricting our attention to values bigger than 0. Notice that the denominator is always positive. This is positive, so the sign will only depend on what's inside the brackets. Jennifer's asking, shouldn't X stop at 1,000? I claim that it doesn't have to stop at 1,000, right? If X is 1,000,000, then Y is going to be very small, right? So you're going to get a very thin field where X could be 1,000,000. And in that case, Y is going to be 1 over 1,000. And that still gives you an area of 1,000. So X could be as large as you want. Inversely proportional, Y will be very small to compensate. Why do we include 0 in the derivative chart? Because I don't want to take anything less than 0, right? Your domain here, this stuff doesn't belong there. So what's going on? If you take a value very small, like 1, the whole thing is negative. And if you take a large positive number, X squared is as large as you want it, minus 1,000 is still going to be a very large number. So you see what's happening. We have a absolute minimum occurring at 10 root 10. The question was asking for the dimensions, so X is 10 root 10. And Y is 1,000 over 10 root 10. This cancels out. If you multiply by root 10 over root 10, this, that, and that cancels out, and we get again 10 root 10. So in fact, what you have is a square. The square minimizes the perimeter. Well, Elizabeth is asking for minimizing a rectangle. Well, the dimensions always give a square. It depends what you're minimizing, right? Here we were minimizing the perimeter. So if you minimize the perimeter relative to a fixed area, you can show that it's always a square. Benjamin doesn't understand why the critical point is 10 root 10 when you thought it was just 10. Why 10? A square is a rectangle, as Kamal suggests, relative to Jennifer's question. The critical points here we are solving when x squared minus 1,000 is equal to 0. So x squared is 1,000, and x is the square root of 1,000, right? Which is 100 times 10. Square root of 100 is 10, so it's 10 root 10. Well, Jennifer, if you are giving the added condition that x cannot be equal to y, then in that case, you would not have a minimum. You would not have a minimum. The minimum would never be attained. Right, because here we're showing that the minimum is a square. So really what you're saying is you're getting as close as you can to this without ever attaining it. but as you get closer and closer, the perimeter, the area, no wait, the perimeter is decreasing. So you're getting a smaller and smaller and smaller perimeter as you are approaching the square without ever reaching it. Why did we not include 0? If x was 0, you don't have any area. If x is 0, the area is 0, not 1,000. So x is not allowed to be 0. Consider this. A box with open top is to be constructed from a square piece of cardboard. Oh, let me write it. A box with open top is to be constructed from a square piece of cardboard (3 feet wide. By cutting out a square from each of the 4 corners, and bending of the sides. Find the largest volume. Find the largest volume such a box can have. You know what's happening, right? You've seen this before, have you? Right, so you're starting with a square. Exactly. And then you're going to cut out small squares around the corners. Right, cutting out a square from each of the 4 corners. So if you cut out a square from each of the 4 corners, there we go. And then you're going to fold these things. And since the squares were all the same size, right? I mean, you have this nice box. Right? Bachelor of Arts and Crafts. Very nice. Very nice. But you know, I mean, you understand. I took out small squares. What if the squares were larger? Right. So you have this square that you're starting out with, 3 feet by 3 feet, and then you're going to cut out squares out of each of the corners. And you know, they could be large squares, they could be small squares. The question is, how large must the squares be to maximize the volume? So as Kamal suggested, we don't know how large the squares are. So let's introduce some variables. How large are these squares? We don't know. Let's call them x. So if you cut out a square of sides square x by x, out of each of the corners, how large, right? I mean, you started out with a side 3 feet long. If you cut out an x and an x, how large is the side, right? I mean, once you bring these up, your sides will have length. Used to be 3. You remove 2 of the x's. It is now 3 minus 2x. So one side is 3 minus 2x. The other side is 3 minus 2x. And the height of your box is exactly as Michael suggests. Right? The volume of your box, 3 minus 2x, that's one side, times the other, times the height. Right? The height is going to be x. This side is going to be 3 minus x. That 3 minus 2x. That side is 3 minus 2x. So 3 minus 2x, 3 minus 2x times x. Exactly that. Now, again, being a physical problem, we don't want to cut out a square with negative length, right? So x is going to be at least 0. How large can it be? How large can your square be? $1.5. Exactly that, right? You cannot cut a square bigger than 1.5 feet because it's going to overlap on the other. Well, so Matt brings up the interesting point that x cannot be 0 or you would have no volume, and x cannot be 3 over 2 for the same reason, because then you'd have no volume. And fine. It actually doesn't really matter. Whether you go with open or closed, it doesn't really matter. I like to go with closed because, as you know, a continuous function on a closed and bounded interval attains an absolute max and an absolute min. So you're guaranteed that you're going to have an absolute max and an absolute min. On an open interval, you're not guaranteed that. But at these endpoints, the volume is 0. And you have well understood that if your squares are very small, you do have a positive volume. So the endpoints will not play a role. So what am I saying? Open brackets, closed brackets, it doesn't matter. Because the endpoints are not going to be where the important things occur here. Not when you're maximizing, at least. Right, so we want the largest volume. Here is the volume. So you know what to do. Maybe we want to expand it first. I don't know. No, let's not. Let's go ahead and. Do you have to state that on an exam? On an exam, whether you take closed or open, I think will be fine. Whatever you want to do. I prefer the closed, but I understand people like the open. But if it was asking you for max or min, then yeah. Let's differentiate. You know how to differentiate. This is the product, so product rule applies. There it is. And let's factor out a 3 minus 2x, leaving us with minus 4x plus 3 minus 2x. So we see critical points. X is 3 over 2 coming from the first one, or 1/2, thank you, Michael, coming from the second. All right. Let us draw first derivative chart. Critical point of 1/2 and 3 over 2. If you take a value very close to 0 here, this is going to be close to 0, that's going to be close to 0, so this stuff is going to be close to 3. And so will the other one. In other words, positive. And if you plug in perhaps a 1, 3 minus 2 is 1, so that's positive. 3 minus 6 is minus 3, so that's negative. Positive times negative is negative. So you see that we have an absolute maximum occurring at 1/2. What was the question asking for? The volume. Find the largest volume. Very well, so we should answer that. Largest volume occurs when and x is 1/2. So you're cutting out a square of length 1/2. And in that case, right, again, we really need to answer the question. And the question is asking us for the largest volume. We'll discuss the volume formula in a moment there, Morgan. Let's just plug in x equals 1/2. So when x is 1/2, this is 1. 3 minus 1 is 2. 2 squared is 4. Times 1/2 is 2. Absolutely. Thank you, Elizabeth and Zoe. Morgan wanted us to discuss the volume formula. We are cutting out a square of sides x from each corner, right? So imagine bringing that up. That's going to be your height. Your height is x, right? So you're going to have a base, which is this, with the sides lifted up like we did. So this side lifted up has length x, and we took an x out here, we cut that out, and we cut another x out here. So what's left, you had 3, and you removed 2 of those x's. So this side has length 3 minus 2x. This side has length 3 minus 2x. And then you have the height of x. So 3 minus 2x times 3 minus 2x times x. That's our volume. How are we doing here? Questions? Anyone? Seems like why can't the x be bigger than 1.5? Well, you're cutting out 2 squares out of a side that has length 3 feet. So if you take a square which is bigger than 1.5, you're going to already overstep onto the other half of the sheet, so you won't even be able to cut out a square of the same size as the original. Wouldn't the answer be 4.5, Benjamin? I'm not sure where you're getting that. We saw that the max occurs when x is 1/2. Just plug in 1/2 into this. It's not 4 plus 1/2, it's multiplication here. It's 4 over 2. And it's squared because of length times width. Exactly that. Questions? Sophia, the absolute max is not 1/2, but it occurs when x is 1/2. And that, right, so largest volume occurs when x is 1/2, and you plug that in, you plug 1/2 into this, and you get 2. Exactly that. Convinced? How are we doing? Questions? Perhaps a good place to end then. We'll pick this up again on Wednesday. Thank you all for coming. Thank you all for coming, and I will see you then. If you have issues concerning the midterm, please contact Isabella or Sean. Thank you very much. You guys have a good one.